All right, welcome to this explainer. Let's get right into it. Every single day, our digital lives demand more and more from the physical world. You know, the emails we fire off, the 4K movies we stream, the crazy, complex AI models we're all playing with, they all live up in the cloud. But as we know, the cloud isn't actually floating up in the sky, right? It's housed in massive, physical data centers. And these facilities face a genuinely massive challenge. They have to balance absolutely staggering power demands with the need for modern software integration, basically just to keep everything running smoothly without literally melting down. So today we're going to unpack some fascinating research on how revolutionizing the way we map and monitor these buildings can just dramatically boost their efficiency.
So here is our roadmap for the explainer. First, we'll look at the data center energy crisis. Then we'll talk about measuring efficiency with PUE. Third, we'll explore the disconnect between BIM and BMS. After that, we'll look at the direct integration solution. And finally, we'll wrap up with a real-world case study.
Kicking things off with Section 1, the data center energy crisis.
Okay, let's dive into this. Why do data centers actually consume so much power? You might think it's just the servers themselves crunching all those numbers, but the real energy hog? It's the infrastructure keeping those servers alive. We're talking massive air conditioning, intense ventilation, and heavy-duty power supplies. Cooling all this IT equipment takes a staggering toll on our global power grids.
And it really all comes down to this one critical threshold, 27 degrees Celsius. Well, actually, scratch that, it's more like the danger number. The energy consumption of your IT gear is directly tied to the power sucked up by the cooling fans. As the heat inside a server rack climbs, the equipment literally has to work overtime pulling in huge volumes of cool air just to survive. In fact, research shows that when rack temperatures push past that 27-degree mark, a server's electricity consumption can rapidly spike by up to 20%. That is a massive hit to efficiency.
Which brings us to Section 2, measuring efficiency with PUE.
So, knowing that heat is our absolute biggest enemy here, how does the industry actually quantify these costs? Well, the gold standard metric is PUE, which stands for Power Usage Effectiveness. It's a simple ratio. You take the total power entering the facility and divide it by the power that's actually being used by the IT equipment. Since that facility power includes all the overhead, like that massive cooling we just talked about, the ratio is always going to be greater than 1. The key takeaway? A lower number means a much more efficient data center. When you map these PUE levels out, the contrast is super stark. Up at a PUE of 3.0, you're looking at a very inefficient facility, meaning only a tiny fraction of your expensive power is actually doing computing work. But to hit that top-tier, very efficient 1.2 level at the bottom, facilities absolutely have to rely on rigorous, constant control of temperature and humidity. Without insanely accurate heat monitoring, hitting that 1.2 is pretty much impossible.
Moving right along to Section 3, the disconnect between BIM and BMS. Now, if monitoring is so absolutely crucial, why are so many facilities struggling to pull it off? Well, it essentially comes down to a clash between how they're built and how they're operated. Traditionally, a data center is designed using a 3D Building Information Model, or BIM. But then, for day-to-day operations, they create a totally separate 2D Building Management System, or BMS. So you have one engineer drawing a diagram and somebody else manually typing those exact same parameters into a completely different system. It's a total duplication of work, crucial spatial data gets lost, and honestly, it just leads to major tracking errors.
Now, what's really interesting about this slide is the sheer contrast between the two approaches. The old traditional method basically forces a duplication of manual effort. You're designing over in one silo and trying to manage sensors in another. But the proposed method completely bypasses that. It says, hey, let's design the facility directly in that rich 3D BIM environment and then use facility management software to link that digital model straight into the operational system. It creates one single unified source of truth.
All right, on to Section 4, the direct integration solution.
Let's look at exactly how this breakthrough methodology bridges that gap. You can kind of think of this as creating a digital twin. Engineers do their design directly in BIM, but then they create custom digital families for the sensors, complete with all the specific manufacturer codes. Then, they connect these digital models straight into the facility management software, linking them to the actual physical sensors in the real world. This direct connection is brilliant because it skips over the flaws of standard exchange formats like COBie files, which often completely drop the dynamic sensor data we need.
So what this does is build this continuous living loop of real-time information.
You have your physical, humidity, and temperature sensors sitting right inside the server racks. Those connect to expansion boards, and then that data flows via TCP/IP straight into the central control room. Literally zero manual data entry. The physical environment is just talking directly to the 3D digital model, archiving the data and plotting the charts automatically.
Let's see how this plays out in the real world with Section 5, a case study on the JSC Croc project.
So, does this whole digital twin thing actually work in the field? Well, the JSCR Rogue project definitely proves it does. Just take a look at this digital map of 18 active server racks. And this brilliantly illustrates the careful placement of 54 temperature and 5 humidity sensors. They're specifically set up in the cold aisles where the air comes in and the hot aisles where the exhaust blows out. Because everything is directly integrated, if a sensor catches a temperature spike, the operator doesn't just see a warning line on a spreadsheet, they see the exact 3D spatial location of the problem area. And the efficiency gains they saw from this were huge. Just by eliminating that disconnect between the design and the operation side, they achieved a solid 25% reduction in total engineering work. We're talking a drop from 80 manual hours down to just 60. Plus, approval times across related systems sped up by 50%, and the time they used to spend checking for physical intersections between different engineering systems cut exactly in half. All those tedious manual updates were just completely wiped out of the workflow.
The ultimate value of this direct integration is moving your facility away from being reactive and disjointed to being fully automated and spatially aware. As the research notes, it ensures that any physical change is instantly duplicated in the digital model. This allows for immediate, precise detection of any deviations, and it instantly notifies the operator the second anything goes wrong. It's a real game changer. We've seen how directly linking a 3D digital model to real-world sensors can completely revolutionize a data center, right? It saves time, saves money, and drastically cuts down on energy waste. But it leaves us with a really fascinating thought to take away. If a single direct integration can slash a highly complex data center's operational waste by this much, what happens when we scale this digital twin model to hospitals, to skyscrapers, to literally every smart building on our power grid? The potential for global energy efficiency is just staggering. Thank you so much for joining me for this explainer, and keep questioning how the digital world can optimize our physical one.